Welcome again. Now let's continue chapter 8 Exergy. Now in the upcoming classes we'll try to understand how can we calculate the exergy of a closed system, exergy of an open system, how can we apply the exergy balance for whether it is a closed system or an open system, and lastly how can we apply the concept of exergy for calculating various numericals for various engineering problems, right? So let's start with the exergy of a closed system, right? How can we calculate the exergy of a closed system? Now consider a closed system. Closed system mean the heat can flow in or out from the system, right? That's the work and heat interaction between the system and the surrounding. So let's say the environment condition is T naught P naught and the system temperature is initially, let's say, T and pressure is P, right? And the both, this is the total system, overall system mean closed system and the environment, right? And the boundary of the overall system, right, this dashed line is the boundary of the overall system. Since for the overall system the total volume remains constant and no heat, since this is an isolated system, so no heat can move in and out from the overall system. Now so what we have defined up till now, that overall system mean closed system, right? A closed system and the environment, right? Closed system and the environment is known as the overall system. No heat transfer to the overall system, that is QC is equal to 0, right? And if we connect, let's say any device, right, then we can get some WC maximum value from the overall system, and the total volume remains constant. If the system expands, if the volume of the system increases, then the volume of the environment will decrease, whereas the overall volume of the overall system remains constant, right? So let's first apply the energy balance for the overall system, right? So if we try to apply the energy balance, which is delta EC, C for overall system is equal to QC minus WC. Since QC is equal to 0, so this term is equal to 0 because no heat can move into the overall system, so this value we can neglect. So remaining is delta EC is equal to minus WC, where WC is the exergy of the overall system or the maximum theoretical work, which is also known as exergy. So in order to calculate this value exergy WC, we have to calculate change in energy of the overall system. So change in energy of the overall system is equal to change in energy of the closed system plus change in energy of the environment. So change in energy of the system is further equal to change in internal energy, change in kinetic energy, change in potential energy. So this is for this system. So likewise we can apply for the environment, change in internal energy, change in kinetic energy, and change in potential energy for the environment. So if we split this, change in internal energy for the system mean final internal energy minus initial internal energy. So for system, the final internal energy is the environment. So environment internal energy minus the system internal energy. Similarly for the kinetic energy, final kinetic energy minus initial kinetic energy. Similarly for potential energy, final potential energy minus initial potential energy. Whereas for system, the kinetic energy and the potential change in kinetic energy and potential energy is equal to 0, right? And the only term that will be remain for the environment is change in internal energy. Okay, then the remaining term is like U naught minus U plus, same for the environment, this term can be neglected, same for the environment, this term can be neglected. So the remaining is minus KE and minus PE plus delta U for the environment. Now we have to calculate this term first, change in internal energy for the environment. How can we calculate this? We can calculate this by using the concept of TDS. We know that dq is equal to dw plus du, whereas dq is further equal to TDS, and the work change in work is P delta V plus du. So TDS concept can be used here. Since we want to calculate for the environment, so this equation we have to apply for the environment, right? So environment mean the temperature should be T naught, delta S for the environment, change in internal energy for the environment, and the pressure for the environment. Similarly, change in volume for the environment. For the environment mean final volume minus initial volume. So in that case, for the environment, final volume will be for the system and the initial volume is for the environment. So this so we need that delta E term, we need this term. So from here delta E would be equal to T naught delta SE minus P naught V minus delta V. Okay, so continue. Now again, now we have no new term now, change in internal energy of the environment. Now first we have to calculate this term again for equation 3. So let's use the entropy balance for the overall system. We know that the entropy balance for the overall system is equal to the entropy transfer because of heat plus the production term, right? And the overall change in entropy of the overall system is change in entropy of the system plus change in entropy of the environment, because this term is equal to 0, because QC is equal to 0. So the change in entropy of the overall system is change in entropy of the system plus change in entropy of the environment is equal to sigma. Since we need change in entropy of the environment, so we need this term only. So this term will go on the other side. So minus delta S plus sigma, right? So now we can put this value in equation 3. So this is equation 3. So if we put that value in equation 3, then delta UE would be equal to minus T naught S naught minus S plus sigma T naught minus P naught V minus V naught. Now we can put that value in equation 2. So basically we need that value delta U environment. So we can put that value in that equation. So finally delta UE would be equal to minus T naught S naught minus S plus sigma T naught minus P naught V minus V naught. So finally, once we will have all the term in that equation 2, so since these term plus this one we have calculated now, so finally change in energy of the overall system would be equal to that equation, and this change in energy of the overall system is equal to Exergy. So Exergy is equal to minus delta EC. So Exergy of this system is equal to minus delta EC. So if we multiply this whole equation with negative, we'll get the equation for the Exergy. Normally we represent Exergy with the help of phi. So phi is equal to WC, which is the Exergy, that is equal to change in internal energy plus P naught V minus V naught minus T naught S minus S naught minus sigma T naught plus kinetic energy plus potential energy. Normally for the reversible system, we can we ignore the term sigma for the reversible system. Similarly, if this system is static, so there is no change in kinetic energy and potential energy. So the simplified form of the Exergy phi would be equal to U minus U naught plus P naught into V minus V naught minus T naught S minus S naught. So from this equation we can calculate the Exergy of a closed system. So Exergy means work potential of any system. What we need is basically we need two state. One is the system state, I mean internal energy of the system state, specific volume of the system, and the entropy of the system. And the other one, the property what we need is we need the reference, I mean the environmental property, like what is the state of the system at environmental condition, right? This is the state of the condition for the environment condition. Normally the properties that are given in the property table, they are specific property, right? I mean the absolute property, they are not available. We have to multiply with the mass then we can get the total value of that. So specific exergy, normally it is represented with small e, so that's U minus U naught, right? So that's a specific internal energy. Similarly, this is specific volume, this is specific entropy, right? So the unit of the energy would be now kilojoule per kg. Energy and exergy, they have the same units. Let's say if the system changes state, let's say from state 1 to state 2, let's say we had a system, let's say this is the system, right, and this is the environment. Let's say the environment temperature is T naught and pressure is P naught, right? So initial state of the system was 1, right? Now the system has changed its state. Now the system is at state 2. Now what is the change in exergy? Now let's say when the system was at state 1, with reference to the environment, its exergy was U1 minus U naught, V1 minus V naught, S1 minus S naught, similarly V1 square, GZ1. So this was when it has a state 1 with reference to the environment, right? Let's say now the system has changed its state, right? State 1 to state 2. Now what's the new exergy? New exergy, let's say E2 would be now U2, V2, S2, right, V2 and Z2. So this would be the exergy of the system at state 2. So E1 is the exergy at state 1, E2 is the exergy at state 2. Now what's the change in exergy? E2 minus E1. So that means, so this is the exergy at state 1, this is the exergy at state 2. So what is the change? You just final minus initial. So final minus initial, so it would be U2 minus U1, V2 minus V1, right, S2 minus S1. So similarly, the change, difference of the kinetic energy, difference of the potential energy. Now this equation is based on that there is no sigma term, I mean sigma T naught, right? We assume that the process is, let's say, steady state process, right? So we assume that, let's say, the process is a steady state, right? So that's why we have ignored the term sigma T naught, right? So this was the specific exergy. Now we can apply this concept for solving different numerical. Now if you see the first numerical, let's say what is the exergy of 2.5 kg of steam at 500 degrees C, 1 megapascal pressure at a height 1.4 meter above the ground level. Assume the environment condition to be 25 degrees C and 1 atmospheric. Now this is a very simple example that if you have a steam, right, this is a steam, let's say at 500 degrees C and 1 megapascal, and the mass of the steam is, let's say, 2.5 kg. What is the work potential? I mean that steam, how much work, useful work output you can get from that steam. Okay, so this is the meaning of the exergy or the work potential. So I mean you will use the same equation that you have derived. Okay.